This video will look at compression. So compression is reducing the size of a file. Now why might we want to do that? Well, we want to make the most efficient use of storage space. So if you reduce the size of a file, that obviously is going to use up less storage space. Also, we might want to have an improved online experience for users, for network users. So if you reduce the size of a file, then those files will download faster because there's less data to actually transport. You can say the same for streaming files, so video and audio files. Again, if they are compressed, then there should be improvements in performance of streaming. Now the two ways that we can reduce the size of a file is lossy compression and lossless compression. Now lossy compression is where there's certain bits of data from a file that is removed permanently. So an MP3 is an example of lossy compression. So this is where a sound file has had certain bits of its data removed. Now, generally speaking, it's not noticeable for the listener. Often it is frequencies of sound that are removed from the file. But nonetheless, lossy compression is where data is removed permanently and not put back again. Lossless compression is where data is temporarily removed from the file, but it might be added back to the file when it's to be used again. So you can have zip files, for example. They are an example of lossless compression. You can zip up a file. It will look for patterns in bits of the data, and if it sees some patterns there, it may well remove that data, remembering what the pattern is, so that later, when it needs to be unzipped or extracted and put back into its original state, that part of the file can be rebuilt again. So lossy compression. Already said this is when data is removed permanently from a file. So we talked about MP3, certain frequencies that aren't noticeable to the user may well be removed, or the data that refers to that may be removed permanently. It doesn't really reduce the sound quality because human beings wouldn't be able to hear those frequencies anyway. Nonetheless, the size of the file reduces. When you're chatting online, or when you're chatting over a mobile network, again, lossy compression is used to reduce the size of the audio files that are, or audio data that's sent across. So it reduces bandwidth. It allows, obviously, for the data to be sent fairly quickly. It reduces it to a certain a poorer quality, but doesn't really affect the ability for someone to understand one another. But it just makes sure that we are making more efficient use of bandwidth. And images are often compressed using lossy compression. So generally speaking, details of images are lost. Parts of or data about the image is completely removed, but only if it can not impair the overall quality too much. So lossy compression might be used on websites for certain pictures, on home pages. Obviously, if the file size is smaller, it means the page will load quicker. And providing it doesn't seriously affect the quality of the image, then obviously lossy compression is very good in those situations. Now, it must be noted that lossy compression results in a much smaller file compared to lossless compression. But lossless compression has many benefits over lossy compression. Ultimately, the data isn't permanently removed. It's only removed whilst the data is being stored or transported. So, lossless compression. Data is temporarily removed, but later on, that data is sort of recreated to put the file back in its original state. So this type of compression will look for sequences of data stored within the file. It will construct an algorithm that can later reconstruct that file by reproducing the sequences of data. Now that might not make perfect sense at the moment, but we'll have a look at some examples of that in a minute. Now this type of compression doesn't remove as much data, like I said before, as lossy, but it does still reduce the size of the file, and of course it retains that data for later use. So two examples of lossless compression. The first one is run length encoding. So we've said before, with lossless compression, it often will look to see patterns of bits within a file, a data file, that it can remove, and then if it remembers what that pattern is, later on it can reconstruct the file to its original state. So if you consider this image of a smiley face, it's a 1-bit image, so each of those pixels is represented by a 0 or a 1. If you take that second line, you can see that there are 5 white pixels in a row. So if we take the second row, the data would ordinarily be 5 bits in length. Here I've said 5 zeros, it probably should be 5 ones actually, because 1 represents a white pixel in a 1-bit image, but anyway. Let's just go with this because obviously I'm trying to prove a point here about what run length encoding is. So we've got 5 white pixels in a row. That would be 5 bits in length with a 1-bit image. Now run length encoding would see that pattern, and what it would do is instead of storing it as 5 bits, it would store it as the number 5, which is how many bits there are, and then the actual bit for each pixel, which would be 0. So it would be 5 whites, or 101, 5, and a 0 for white in this case, which uses 1 fewer bit. So 101, 0 is 4 bits. That is 1 less than the 5 bits in the original image. So that's the principle of run length encoding. Now obviously that doesn't seem like a great reduction, but if you were to consider a larger image with many more patterns of similar shades, we can use run length encoding to drastically reduce the size of the image file. So dictionary coding is another example of lossless compression. Now this is where we look to replace the data stored within a file with a reference to what the data is. So imagine that you've got a dictionary that contains all of the words of the English language, and imagine that that dictionary was in a table and each word had its own index location. So aardvark would be at index 1 and so on. Now let's have a look at this example of a sort of an excerpt from the dictionary. We see that we've got the word computer, which is at index location 24. We got the letter I, which is at 54. We got love, which is at index 85. We've got science, which is at index 99. And then consider that we got the following string, which is 23 bytes in size. I love computer science. 1 byte for each character. So with dictionary coding, these words could be replaced with their reference, their index location in the dictionary. So the data would be stored whilst being compressed as, well, the letter I, okay, is at index 54. So that in binary is 110, 110. So instead of storing the letter I as a byte, we can store it with just 5 bits for the number 54, or a byte anyway. But let's look to the next one because this is more important. If you look at the word love, that obviously would usually be 4 bytes in size, that word would be. However, if you look in the dictionary, love has got the index location of 85, and we just need 1 byte to have that to represent that number 85 as 1010101. There you go. And we could say the same with computer. Computer would ordinarily have for 8 bytes to store all the letters in computer, but instead we could replace that with the number 24, which is its index location in the dictionary. So the data would be stored whilst being compressed with just 25 bits, which is far, far smaller than 23 bytes worth of data. So yeah, the dictionary would have to accompany the compressed file, but for large text files and documents, the size of the dictionary wouldn't have that big an effect of the overall size of the file once it's compressed. And that's an example of dictionary coding.